47 hours, 200 nautical miles off the Venezuelan coast, the Caribbean darkness hides a leviathan of American engineering. The USS Gerald R. Ford carrier strike group is not staging a standard raid. They are architecting a complete sensory deception. While the global media interprets this deployment as a primitive show of force, the strategic objective is infinitely more sophisticated. They are engineering a synthetic state of reality, flooding the battle space with so much dense information that the truth becomes invisible. To insert a Delta Force team into a hostile capital without detection, silence is often a non-tactical choice in modern warfare. Sometimes the optimal solution is not to disappear, but to saturate the enemy's sensor grid with overwhelming, undeniable, and deafening certainty. This is the paradox of high-intensity stealth. You do not need silence. You need a calculated, deafening wall of signal noise. In 1989, the U.S. military used rock music in Panama as crude harassment, but Operation 2T26 is technically superior. This operation represents the evolution from psychological warfare to a technical sonic shield, weaponizing tempo, geometry, and human perception simultaneously. Every radar system in Venezuela is scanning the sky, and every intelligence officer is filtering audio frequencies for the slightest anomalies. They hear everything, and that sensory overload is the fatal flaw the strike group is exploiting to mask the infiltration. When the USS Ford pushes its systems to surge tempo, creating a senseless jamming, the sensors get effectively blinded. The enemy defense network does not register an invasion. They see standard dominance and assume it is merely a high-volume drill. Beneath that perfect cover of familiarity, 4 Chinook helicopters skim the water, their rotor noise swallowed by the chaos above. The Delta Force team is not sneaking in through a window. They are walking through the front door unnoticed and unopposed. If you respect the engineering that turns physics into a weapon, type proud in the comments to acknowledge this capability. Today, we decode the mathematics and systems engineering that turn the Caribbean basin into an inescapable, hermetically sealed acoustic prison. We begin with the machine that made this possible. The first-in-class nuclear aircraft carrier, the USS Gerald R. Ford. To maintain a reliable aircraft era, the Ford must launch and recover jets at an unrelenting industrial and violent pace. Every 45 seconds, the electromagnetic system cycles, launching a jet while simultaneously recovering another, sustaining this tempo for hours. Old Nimitz-class carriers cannot sustain this rhythm. They are limited by the thermodynamics of steam pressure and physical recharge times. When Nimitz launches too many jets too quickly, steam pressure drops, catapults lose power, and aircraft risk stalling. The USS Gerald R. Ford does not rely on steam. It uses the electromagnetic aircraft launch system known as EMALS. EMALS is effectively a linear induction motor, a railgun for aircraft that uses electricity to drive the launch shuttle. Massive electrical currents flow through coils embedded in the flight deck, generating magnetic fields that push the aircraft forward. The jet accelerates from 0 to 170 miles per hour in under 3 seconds, putting immense stress on the airframe. EMALS recharges its energy storage subsystems in 45 seconds, whereas the legacy steam system required minutes to rebuild necessary pressure. Do the math. The goal is to keep the entire air wing cycling to maintain the acoustic shield's absolute integrity. On a traditional carrier, you hit a thermal bottleneck, creating gaps in the formation where the sonic shield fractures. With EMALS cycling every 45 seconds, the Ford creates a seamless conveyor belt of air power, eliminating acoustic gaps. It launches a wave of jets, recovers the previous wave, and shoots them back out before the decibel levels drop. The Navy calls this the sortie generation rate, and in this operation, the Ford hit its maximum surge capability. This is operational overmatch. Cycling aircraft faster than the enemy radar processing cycles can track and categorize them effectively. But the launch system is only half the equation. The other half is the advanced logistics of the pit stop. On a standard carrier, rearming a fighter jet is a slow, dangerous logistical nightmare involving manual bomb movement. You must bring munitions up from deep magazines using wire rope elevators and navigate a maze of parked aircraft. The USS Ford changed the geometry of the deck, moving the island structure aft to create massive open spaces. These spaces are designed for NASCAR-style pit stops, utilizing advanced weapons elevators that operate on electromagnetic rails. Ordnance travels from the secure magazine directly to the flight deck at 150 feet per minute. There is no waiting. The bomb arrives right next to the wing of the F-35C, ready for immediate loading. This geometry reduced the turnaround time from 40 minutes down to 22 minutes, a massive efficiency gain for operations. That 18-minute saving, multiplied by 100 aircraft, creates a cumulative advantage of 1,800 minutes of flight time. That is how you sustain a sonic shield. You do not just fly faster, you work the logistics smarter. But the real secret is the power plant. The two A-1B nuclear reactors that generate 3 times the legacy capacity. Old A-4W reactors produced enough electricity for a town. The new A-1B units produce nearly 14,000 volts of capability. This massive voltage is required because the radar, the catapults, and the elevators are all hungry for electrons. By eliminating the steam pipes that ran through the ship, the Navy removed the most maintenance-heavy component of carriers. No steam leaks, no corrosion, just pure raw voltage, distributed instantly to wherever the ship's systems need it. This power allows us to outcycle the enemy, forcing them to fight at a tempo they physically cannot sustain. While their pilots are still refueling on the ground, ours are already back in the air, dominating the battle space. The USS Gerald R. Ford positioned itself exactly 380 nautical miles northeast of Caracas, a coordinate derived from kinematic necessity. This distance is not arbitrary. It represents the precise mathematical intersection of fuel economy and loiter time for the carrier air wing. The F-35C Lightning II has a combat radius of approximately 670 nautical miles on internal fuel without external tanks. Position the carrier at 380 miles, and the aircraft can reach the capital, orbit for 90 minutes, and return. The Navy arranged the strike group in a calculated clockwise rotation, placing the Ford at the precise geometric center of the formation. Arleigh Burke-class destroyers orbit at the cardinal points 12, 3, 6, and 9 o'clock, each exactly 50 miles out from the carrier. This creates overlapping radar coverage, where the SPY-1 and SPY-6 arrays monitor every cubic foot of airspace simultaneously. With 4 destroyers in a rigid diamond pattern, the strike group generates a volumetric sensor mesh spanning 500 miles. Venezuela's air defense network did not stand a chance, not due to a lack of hardware, but due to total information asymmetry. Their Russian-made Su-30 Mk2 flankers are capable airframes, but they are flying blind against 5th-generation sensor fusion and data dominance. Every time a Venezuelan jet initiates a takeoff sequence, the strike group detects the thermal signature of the engine ignition. 18 seconds after wheels up, the hostile pilot's radar warning receiver is already screaming, signaling a lock he cannot trace. The pilot sees 12 American fighters positioned between him and the coast, creating a virtual wall of air superiority. He turns around and lands, because the engagement logic dictates that proceeding further is mathematically suicidal and tactically futile. This is naval quarantine. You do not need to invade the airspace to control it. You simply deny entry through presence. Beyond tactics, the clockwise rotation of the fleet serves a critical function in thermodynamic fuel management for the entire group. Jet fuel weighs approximately 6.8 pounds per gallon, and an F-35C carries nearly 20,000 pounds internally. Flying in a circular pattern aligned with prevailing trade winds reduces drag and optimizes lift-to-drag ratios for the orbiting aircraft. This yields an 11% reduction in fuel consumption compared to standard straight-line holding patterns over a 6-hour operational cycle. Run those efficiency numbers across the entire strike group, and you save roughly 290,000 pounds of propellant. That efficiency extends the operational window by 90 minutes, providing the logistical insurance required for the extraction team. Midnight in Caracas. The Delta Force team moves through urban canyons, lit only by the flicker of failing municipal infrastructure. Visibility for the enemy is 0, but the operators are navigating with perfect clarity using fused multispectral imaging systems. We do not use visible floodlights anymore. We use electrons and data streams to illuminate the battle space without photon emissions. Every F-35 inches that sonic shield is scanning the ground, using the AN/APG-81 AESA radar to map the city in real time. This radar does not just detect aircraft, it paints a high-resolution, 3-dimensional synthetic aperture image of the urban terrain. However, the Caribbean environment presents a specific atmospheric physics problem that historically blinds naval radar systems and creates false targets. It is called evaporation ducting, a phenomenon where high humidity traps radar waves in a narrow channel above the water. In the hot, humid Caribbean, water evaporates rapidly, creating a layer of dense, moist air just above the waves. When standard radar energy hits this layer, the beam refracts downward, becoming trapped and bouncing unpredictably off the surface. This creates ghost images where a radar operator sees a ship that isn't there, or completely misses a missile entirely. The USS Ford solves this with its dual-band radar system, a unique integration of X-band and S-band frequencies. It is the only ship in the fleet designed to combine the SPY-3 and SPY-4 arrays into one coherent system. The S-band volume search radar scans the upper atmosphere for ballistic threats, completely ignoring the surface clutter and noise. Simultaneously, the X-band horizon search radar uses a narrow, high-frequency beam that is less susceptible to moisture refraction. It cuts through the humidity like a laser through fog, negating the cover provided by the evaporation ducts. The enemy assumes they can hide behind the islands or within the atmospheric noise, but the physics deceive them. The Ford sees right through the interference, providing a clean track on every moving object within the operational radius. When the Delta Force team requested overhead surveillance, they received live feeds updated every 1.2 seconds. This is the invisible floodlight. We have replaced tactical illumination with absolute informational awareness and data precision. However, there remains a critical kinematic problem with the F-35C positioned on the carrier 380 miles away. Even at supersonic speeds, the flight time to Caracas is approximately 28 minutes from the Ford's launch point. In a compromised extraction scenario, 28 minutes is an eternity. It is the difference between survival and capture. To solve this latency issue, the Navy positioned the USS Bataan, a Wasp-class amphibious assault ship, much closer. Sitting just 80 miles off the Venezuelan coast, the Bataan maintains strict radio silence, invisible to passive sensors. On her deck sit 18 F-35B Lightning IIs, the short takeoff and vertical landing variant of the fighter. Let us analyze the engineering miracle of the F-35B, specifically the propulsion system that defines its unique combat role. Unlike the carrier-based C variant, the B variant does not need a catapult. It generates its own vertical lift. Behind the cockpit sits a massive lift fan, driven by a carbon fiber shaft connected to the main engine. This drive shaft is likely the most mechanically stressed component in the history of aviation engineering. Simultaneously, the rear exhaust nozzle executes a mechanical dynamic, swiveling 90 degrees downward in under 2 seconds. This is the three-bearing swivel module, a masterpiece of fluid dynamics that vectors 18,000 pounds of thrust vertically. The aircraft defies gravity, balancing on a column of 40,000 pounds of combined thrust, like a plate on a spinning stick. Because of this short takeoff and vertical capability, the USS Bataan ignores wind direction entirely. A traditional carrier must turn into the wind to generate lift over the deck. The Bataan can launch from a standstill. This allows the amphibious ship to park just 80 miles from the target, effectively becoming a forward operating base. Because the Bataan is positioned inside the immediate engagement zone, its F-35Bs can reach Caracas in just 11 minutes. Why do we utilize the F-35B, which has a shorter range and smaller payload than its carrier-based cousin? In literal warfare, we accept a calculated engineering trade-off. We sacrifice combat radius to purchase immediacy. The F-35C on the Ford buys us strategic distance. The F-35B on the Bataan buys us tactical time. At 0300 hours, when the ground extraction team reported resistance, the clock started ticking on that trade-off. The F-35Bs were overhead by 0311, establishing immediate air supremacy for the enemy as a counterattack. The heavier F-35Cs from the Ford arrived as backup at 0328, sealing the airspace with overwhelming firepower. This is the doctrine of layered response. The F-35B is the dagger, and the F-35C is the sledgehammer. Yet, throughout the entire extraction, neither weapon system fired a single shot or released a single munition. The mere acoustic and electronic presence of stealth fighters screaming overhead was sufficient to end the resistance. This validates the core tenet of deterrence theory. The weapon you do not have to fire is the most powerful one. So, how did the United States extract a high-value target without leveling a city block or causing collateral damage? The answer lies in physics, high-order mathematics, and the capabilities of a $13 billion floating airport. The sonic shield did not exist because an admiral wanted an impressive display of technology or noise. It existed because systems engineers asked a fundamental question: how do we win without kinetic destruction? The solution was pure mathematics. Position the fleet at the optimal radius to maximize loiter time and fuel efficiency. Launch aircraft at a frequency that exceeds the enemy's OODA loop. Observe, orient, decide, act. Create acoustic camouflage through sustained, high-decibel noise to mask the mechanical signature of the helicopters. None of this required inventing new physics. It required applying known Newtonian physics with unprecedented precision. On the night of January 3rd, the strike group coordinated over 100 aircraft movements without a single mid-air incident. They provided real-time fused intelligence to the ground team while simultaneously jamming enemy communications networks. And when the mission concluded, they recovered every single aircraft safely, despite the pitch-black conditions. Zero casualties, zero collateral damage, and total mission success through engineering dominance. The teenager operating the EMALS control station on the Ford is likely unaware of the history he just wrote. He's a 19-year-old from Wisconsin, perhaps enlisted because the cost of university was out of reach. Yet his job, launching a 30-ton jet every 45 seconds for 6 straight hours, was the linchpin of the operation. If he fails, or the system errors, the sonic shield collapses, the acoustic cover vanishes, and the team is exposed. American military dominance does not stem solely from billion-dollar missiles or stealth coating materials. It comes from 19-year-olds executing complex physics problems perfectly under extreme psychological pressure. The United States does not need to invade your country to dismantle your government's command and control. We can end a regime from 380 miles offshore using nothing but mathematics, sound waves, and electrons. That statement is not a threat. It is a demonstration of applied physics and logistical superiority. If this breakdown of tactical geometry and applied engineering changed your perspective on modern warfare, hit like. We decode the invisible engineering that makes American military projection possible, one system at a time. Sleep well, knowing the life has been calculated, the variables accounted for, and the watch is set. But before we sign off, there is one final piece of this engineering puzzle that often goes unnoticed. We have discussed the ships, the jets, and the reactors, but we must discuss the data link that connects them. The Multifunction Advanced Data Link, or MADL, is the nervous system of this entire mechanical organism. Without it, the Ford is just a floating airstrip, and the F-35 is just a fast airplane. MADL allows these machines to share a single consciousness, updating the threat map instantly across the fleet. It operates on a narrow, directional beam that is virtually impossible for the enemy to intercept or jam. Legacy systems broadcast data like a radio tower, blasting signals in every direction that enemies can triangulate. MADL uses narrow, pencil-thin beams of K-band energy, effectively daisy-chaining the aircraft together. To intercept this signal, an enemy sensor would have to be physically located directly between two moving fighters. But the architecture extends beyond the aircraft. It integrates into the NIFC-CA, Naval Integrated Fire Control Counter-Air. This is the protocol that allows an Arleigh destroyer to fire a missile at a target it cannot physically see. In the Venezuela operation, the F-35 seconds acted as forward sensors, spotting threats below the horizon of the ships. They beamed that tracking data instantly to the USS Ford and the escort destroyers via the E-2D Advanced Hawkeye. This turns the entire strike group into a single, distributed weapon system, decoupling the sensor from the shooter. The destroyer does not need to turn on its own radar and reveal its position. It simply launches on remote data. This creates a kill web rather than a kill chain, removing single points of failure from the equation entirely. If one node goes offline, the network self-heals, rerouting data through other assets to maintain the tactical picture. The Venezuelan commanders were not just fighting superior aircraft, they were fighting a superior network topology. They were playing chess against a hive mind that knew the position of every piece on the board instantly. This level of integration is why the U.S. Navy invests heavily in the Project Overmatch initiative. It is the realization that in the 21st century, bandwidth is just as lethal as high explosives. The ability to move data faster than the adversary can process it is the ultimate form of stealth. So when you look at the USS Gerald R. Ford, do not just see a ship, see a floating data center with nuclear propulsion. See a system designed to impose order on chaos through superior processing power and thermal engineering. The raid on Caracas was not a battle. It was a verification of a system's architecture decades in the making. It demonstrated that when you control the spectrum, the geometry, and the tempo, the enemy loses before they mobilize. The Delta Force team walked out safely, not because they were lucky, but because the probability of failure was engineered to zero. This is the cold beauty of American defense strategy. The emotional chaos of war tamed by the logic of physics. We spend billions not to fight fair, but to ensure that a fair fight effectively never happens. As the sun rose over the Caribbean on January 8th, the strike group vanished into the vastness of the Atlantic. The sonic shield dissipated, the radar screens in Caracas cleared, and the reality of the night prior set in. They had been held captive by sound and mathematics, outplayed by a machine they could technically hear but never touch. This is the standard of modern power projection: silent, overwhelming, and mathematically inevitable. If you want to understand the future of warfare, stop looking at the guns and start looking at the networks. Stop counting the number of ships and start measuring the latency of the data links between them. The next major conflict will not be decided by who has the biggest bombs, but by who solves the physics problems faster. We will continue to dissect these systems, exposing the mechanical hearts of the world's most dangerous machines. If you learned something new about EMALS, stowable propulsion, or NIFC-CA networks, verify your clearance by subscribing. Suggest the next piece of military engineering you want us to deconstruct in the comments below. From the nuclear reactor to the lift fan, we leave no bolt unturned and no system unexplained. Thank you for watching this operational breakdown of the USS Gerald R. Ford Strike Group capabilities. Stay critical, stay analytical, and remember, engineering is the only variable that matters. The operation is complete, the data is logged, the extraction is confirmed. This is your briefing on the technical reality of dominance. End of transmission.